I have a couple of questions here. So Anand has asked, ancient people did not have technological precision to determine equal days and nights. There is a time lag between an equinox and a change in the weather. So why the special significance of the equinoxes?
So the equinoxes are easy to pick out in that basically because of that motion along the horizon, right? So as the sun is moving north and south, the rising and setting positions are moving north and south. The equinoxes happen at the time when it's exactly in the middle of that range, right? So the sun rises, rises due east and sets due west, and so those are easy to pick out without needing to do any timing to determine that the days and nights are equal. Now you can also use something like a water clock to determine that and those are also extremely ancient. We have water clocks invented, 4,000 years ago. Those are also very ancient technology that you can use to show that the days and nights are equal length, but you don't have to do it you don't have to use those to find the equinox. You can find the equinox just by the position of the rising and setting sun. And there are I'm forgetting now, there are tons of, I mentioned Newgrange, the title of the book mentions Stonehenge. These are, but the British Isles are covered with ancient monuments that are aligned to particular astronomical events. And there are several that are aligned to the equinoxes. So, there's some passage that is carefully lined up so that the rising sun on the equinox, comes in due east. So that's the technique for measuring.
And Anand also asked, what are your views about GPS satellites and their interference with astronomy, e.g. radio astronomy, not just their physical presence?
So the GPS satellites, right, they're broadcasting their signals at particular frequencies, and that does have the effect of knocking out, right, any possibility of doing radio astronomy at those frequencies. So they interfere somewhat over a wider range, but it does, it is a problem for astronomers. The people who decide on these things, who chose the particular bands of frequency that the GPS constellation broadcast in, there was some consultation with astronomers, and they make some effort to avoid using frequencies that are in the vicinity of frequencies that are particularly useful to radio astronomy. And so, they try to avoid that as best they can. It's a trade-off, and you have to make that. I think the ability to navigate without worry at the scale that you are able to because of GPS supersedes anything that you would lose to radio astronomy. But it is a cost.
Nicholas has asked, how does an unstable nucleus keep time?
So nobody entirely knows. So an unstable nucleus, right? The idea is you have certain kinds of atoms that are just barely holding it together, right? And after some amount of time, they're going to fall apart. A piece is going to go flying off, and we see that as a radioactive decay. There is some characteristic time for that to happen, but the process is inherently probabilistic. So we know that on average, right, if I start with 1,000 atoms, right, on average in the next hour, 10 of them are going to decay, but we can't say which 10, right? And you can say with great precision, what fraction of the atoms will decay in a given amount of time, but you can't say any particular one will last. You can think of it as a sort of process whereby the particles in the nucleus are bouncing back and forth at some characteristic frequency, and every time they hit one of the turning points, there's a chance that they make it out. right? But that's not a frequency that we can really measure directly. And what exactly determines when an individual atom decays is completely unpredictable. And so, we can't really say anything about it.
We've got a question from Cassio, who's asked, how are leap seconds decided?
So leap seconds are decided by there's a group. It's called like it used to be called the International Earth Rotation Service, and they've added something else, so it doesn't sound quite as steampunk and cool. And I forget what the formal name is now, but there is a body that basically tracks the apparent motion of stars. Right. So you look at what time is this star directly overhead, and they monitor that very closely and continuously through the year. And based on that information, they can determine the rate of rotation of the Earth, which is gradually slowing. And it's slowing because of the gravitational influence of the moon. So the same gravitational force that causes tides also causes the crust of the Earth to flex a little bit. And that causes the rotation of the Earth to slow down. And so the Earth is gradually slowing due to this tugging by the moon, and that means that the length of a day is changing. So there's this international body that monitors the apparent motion of stars, and from that determines this rate of rotation of the Earth. As that slowing goes on, when it reaches a point where the year has become 1 second longer as a result, then you can stick in these leap seconds, and that can happen in June or in December. Most of them have happened in December in the 50 years that this has been going on. And it's a little controversial whether this is worth doing, because it's kind of a hassle for the people who maintain software systems and that to have this extra second show up sporadically. But they give people plenty of notice and they do it. But they're every time a leap second is added, there's a discussion about should we be doing this at all? Should we just wait until it's like a leap minute, which will be 400 years from now, and then then it's somebody else's problem.
You answered the question that I was going to ask of how long would it take for these seconds to build up to something that is actually noticeable, but 400 years. Yeah, I say.
I can't swear that that's the actual number. It's probably less than that, but it's long enough that all the people who have to deal with the hassle of the leap seconds now would be retired, and so none of them are going to care.
We've had a question from Rog, who says, will we get to a point in time when we measure to Planck time intervals? Will there be anywhere to go then?
So the Planck time that he asked about is if you take sort of the fundamental constants of nature, so things like the strength of the charge of the electron, the strength of quantum effects, the strength of gravity, you can put them all together in a way that gets you a time that is something absurdly short. It's 10 to the minus 43 seconds, something like that. Really, really ridiculously tiny time. And there are some theories that regard this as kind of a fundamental sort of limit. That there's even theories of space and time in which time is sort of granular on that level. So that it would have no meaning to try and speak of an interval shorter than that would have no meaning. We're highly unlikely to ever be able to measure time at that scale. Right now, the shortest time intervals that we can measure is somewhere in the attosecond range, which is it's a 10 to the minus 18. So it's a billionth of a second, American billions. And that's the shortest interval we can measure. You can go better. You could go a little faster than that, but these are down where you're looking at single oscillations of fairly high frequency light. So it's hard to measure finer than that. there's also the problem that to measure on that kind of scale, you need to be measuring with precision that's, a huge number of decimal places. And, somewhere like well before you get to there, then your time measurements are thrown off by things like, the gravitational attraction of the graduate student who's operating the apparatus. And, are they standing a meter closer or farther away from it? And, once you hit a technical floor that you just can't possibly, can't practically overcome.
Nancy has asked, to what extent do the measurement imperfections or noise in the cesium clock affect timekeeping?
The cesium clocks are really incredibly good. They're good to parts in 10 to the 16. So that means, if it says, 1 second according to that clock is, 1.000, 15 zeros before the first uncertain digit. A huge amount of the business of running atomic clocks, the people who work in these national standards labs that maintain these, a huge amount of their business is understanding those uncertainties and characterizing them and quantifying them and taking them out, right, and figuring out ways to push the clocks to ever better performance by eliminating various sources of uncertainty in ways that are really ingenious. This takes a very particular personality type to do this kind of research. You have to really be into chasing down tiny little effects that have to do with the residual motion of things that are cooled to a billionth of a degree above absolute zero, and how are they interacting with neighboring atoms and things like that. I have the utmost respect for people who have the patience and the personality to do that, and I'm also glad I'm not one of them. So
I know you said it was probably a long lecture, but how do you call something to like almost absolute zero, like for this?
So the idea, it's a wonderfully counterintuitive thing. They use techniques called laser cooling, and the idea is if you bounce a photon off an atom, it exerts a little force on that atom. And bouncing a photon off an atom, well, an atom's only going to absorb and scatter photons of a particular frequency. So then you can play a clever trick where you make the frequency of your laser such that the atom has to be moving toward the laser to absorb the light. And then when it gets a force from the light, it slows down. So you can arrange it so that shining a laser at a very particular frequency on a very particular kind of atoms exerts a force that causes those atoms to move more slowly. Slow equals cold. So if you do this over and over and over, you can cool the atoms, and you can cool them to such a level that it corresponds to the residual motion corresponds to millionths of a degree above absolute zero. And that's basically the atoms in the air around you are moving at something like the speed of sound, and laser cooled atoms are moving at centimeter per second. So.
Wow.
And you can do that just by shining light on it. It's a really amazing technique. There's a whole lot of technical stuff that goes into it. That's the core idea. So.
You're right. It does sound counterintuitive. So AC has asked, if a gravitational wave passes through an atomic clock, does it change its accuracy?
Yes, at a level that's currently imperceptible. So it does. The gravitational wave passing by, right? These are waves in the fabric of space and time, and so we've detected gravitational waves using LIGO, right, which looks for the stretching and compressing of space that happens as the gravitational wave goes by. That same wave is going to cause time to go a little faster and a little slower in a similarly oscillating fashion as it passes through, and you could, in principle, detect that. The current atomic clocks can't. They're not yet sensitive to that, but that's one of the motivations for that slide I had of the clock that's 1,000 times better than a cesium atomic clock. right? Those aren't so necessary for GPS, right? GPS, you can get your position to within a few meters. Having your position to within a few millimeters isn't that much more useful. But having that extra factor of 1,000 or 10,000 or 100,000 gets you to places where you could take a whole bunch of atomic clocks, put them on satellites out in space, and a passing gravitational wave will sort of cause a ripple through that assemblage of clocks that you could detect and pick up the gravitational waves. So that's a thing that people are very actively working on.
It kind of links to our next question, actually. Tom asks, what are the applications of measuring time to a greater accuracy than an atomic clock?
Yeah, a lot of it is exotic physics. So the gravitational wave thing is one. There are certain versions of dark matter would have an effect that would make clocks speed up and slow down in a particular pattern, and so people look for that. There's also, one of the coolest is there's these theories that the strength of fundamental forces could change over time. The constants of nature could change over time in some exotic theories of physics. And so, the strength of electromagnetic forces between things is a little bit higher today than it was billions of years ago. Well, if that's still happening today, that would cause different types of ultra high precision clocks to shift their frequencies in different ways. And so people have done these experiments where they compare like a mercury ion to an aluminum ion, and they look at the frequencies of clocks based on those two things to see is the ratio of those two frequencies changing. If it is, that would indicate that the strength of electromagnetism is changing. The good news is it's not. To the best of any of the measurements that anyone's done to this point, we don't see any change in these constants of nature. But that's a thing that's predicted by certain kinds of exotic theories. And so it's, again, something that people are very actively looking for.
Joanna has asked, is it true that time passes more slowly if one is traveling very fast? And if so, why?
Yeah, there's another whole path through this to talk about, how time is perceived as an individual thing. It's absolutely unquestionably true that that time ticks, the clocks tick at different rates depending on how they're moving. So if you have an atomic clock with you and you watch another atomic clock moving by at high speed, you would say that clock going by is ticking more slowly than the one that you're holding, right? This is the weird thing about this is that the person moving with the other clock would say, no, my clock is ticking at the right frequency, yours is running slow. You each see the other's clock is running slow. And there's absolutely no measurement you can do that will tell you anything other than my clock is right and theirs is running slow. So how much time elapses between two events is going to be different according to different observers, depending on how they're moving. And this is a prediction of Einstein's theory of relativity. This has a deep connection to timekeeping. There's a terrific book by a guy named Peter Gallison. It's called Einstein's Clocks, Poincaré's Maps. And it talks about this connection between relativity and timekeeping. And this is something that's been directly measured. One of these, at NIST in Boulder, Colorado, the group of Dave Wineland there built these aluminum ion clocks. And they built two of them, and they could measure the effect of, in one of them, they held the ion perfectly still and measured its ticking. And the other one, they set the ion moving back and forth at various different speeds, and it ticks slower by exactly the amount that you predict from the theory of relativity. And that holds for speeds that are, basically like a brisk walk, or, like a speed you can move on your bicycle. If you have a sufficiently good atomic clock, you can register that that clock's actually ticking slower.
Cool. John has asked, are the clocks in GPS satellites synchronized? And if so, how?
Yes, the clocks are synchronized. So they have atomic clocks in the satellites that have been launched, and they've been launching these for decades now. They every now and then they replace them. They put new satellites up. The clocks are synchronized. Basically, the orbits are set up so that they pass over, Washington D.C. basically at regular intervals. And there's people there at the Naval Observatory whose whole job is to synchronize the clocks on the GPS constellation and make sure that they're, that they're properly conveying the correct time. So that's all done by exchanges of radio signals that between the satellites and ground stations, and there's a whole very complicated process that they use to take out various errors. I should say that those satellites are also corrected for relativity. So because they're orbiting the Earth, they're moving very, very fast. And that would cause them to run slow compared to identical clocks on the ground by something like 7 microseconds a day. And and the fact that they're at high altitudes in orbit would make them run fast by 40 something microseconds a day. So the combination of those is they would drift off by something like 34 microseconds a day, which is a pretty substantial distance. But the people who made the system knew this. And so those clocks are corrected so that they tick at a rate, if you had one stationary next to you on the ground, it would tick at a rate that's different than a standard cesium atomic clock. But they're made to be in orbit, moving very rapidly, and they keep perfect time that way.
And PJ has asked, does GPS technology exist today with the capability of measuring the distance between two locations in space within the Earth's atmosphere accurate to a micrometer?
To a micrometer? I don't think so. That's very, very small. If you want to know the difference between two locations at that precision, you would do something else. It's like GPS isn't the right tool for that job, but there's all sorts of laser, optical systems that you can use to measure those distances at that level of precision. Some of these lattice clocks, these optical lattice clocks do. There's a recent paper where they say that they have this. It's a set of atoms at slightly different positions that are held in this array of little traps. And they say that if you average together the frequencies of the ones on the bottom and the ones, average together the frequency of the ones on the top, you can see a difference between them. That's caused by their gravity, by the difference in altitude of, a millimeter. So, or less than a millimeter. So they say they can see that with these ultra high precision lattice clocks. Which is really, that's just astonishing.
Sabrina has asked, what factors would future timekeeping methods have to account for if humans were to pursue space exploration?
So the things like the nice thing about atomic clocks is that they're referenced to cesium atoms, or whatever kind of atom we use in the future. They're referenced to atoms, and if you have an atom of the right type, physics guarantees that it will keep the right time. So you could have a clock that you carry with you anywhere you explore that's going to keep exactly the right time and have confidence in that. If you're exploring out in space, right, then you get into questions of like, well, this happens, people talk about like the Mars rovers, right? And there's the teams that work with the Mars rovers, right? They work on these odd times because a day on Mars is a little longer than a day on Earth because the planets rotate at different rates. And so, if your research requires you to be up, when the sun is up on Mars, then you're keeping a weird time. You're sort of drifting out of sync with the rest of Earth because that other planet's rotating at a different rate. So you get into all kinds of interesting questions about, okay, if we're exploring space, we're putting a colony on Mars, who gets to decide what time it is, right? And like when we're it's difficult enough coordinating these Zoom things across the Atlantic, right? But like you at least have the same 24-hour day that I do, right? But you're doing this to an entirely different planet, then things get really weird.
Daniel did ask, how would time work in a multi-planetary system? And I just keep thinking of Star Trek, like, do they all keep the same time? Do they all know what's going on? So yeah, but
at some level it comes back to the, fundamentally time is a matter of convention, right? And so at some level what we're all doing is, you make an atomic clock, and an atomic clock is great for telling you how much time has passed, right? And any time that you measure with a clock, you're counting ticks. You're saying how much time has passed since some particular event. And so, determining what time it is a matter of getting everybody on board to agree on a particular time that we're going to say, okay, that's when we start, and then we run things forward from there. And how you do that would be a matter of diplomatic negotiation between groups, or we're all going to agree that the time, we're going to count time as elapsed according to someone in Greenwich on a particular date, and then we go from there.
And I've been saving the most important question for last. Nancy has asked, what is better, Rolex or Casio?
It depends on what you mean by better, right? Like what kind of watch is better is a hard question. If you mean better in terms of keeping time, right? I have two watches. This one is just a Seiko quartz watch that I've changed the band on it several times, and I've probably spent more on the bands than was spent on the watch originally. I also have an Omega purely mechanical watch. That's an heirloom inherited from a dear friend of the family. It's a marvelous piece of engineering, fantastic things from the 60s. Keeps really good time for a mechanical watch, but the cheap quartz watch keeps better time because I didn't get into quartz technology in this, but it's just they're fantastically good clocks, beyond John Harrison's wildest dreams of a longitude timekeeper. And you can walk into a dollar store and get a watch that's going to keep time better than any mechanical watch like a Rolex. But if what you want is something that gives you the either the satisfaction of having an enormous amount of money, or knowing that the engineering and precision that goes into making those things, that could be more valuable in its own way.
I said I was saving it till last, but then two really good questions came up, and then we can fit them in. So
Sure.
Tom asked, could sundials work in a binary star system, and how would they be manufactured or read differently?
Could sundials work in a binary star system? That's an interesting question. I believe so. I think it would just be like you wouldn't have like a single set of lines, right? Like the sundial, classic sundial picture is you got a stick, and then there's kind of rays going out that say these are the different hours of the day, right? You'd need two of them, right? You need one for each star, and then there'd be some you'd have kind of multiple shadows being cast at any given time, and then you'd have to look at where do they intersect and things like that. There'd be something complicated going on, but I assume it would work. Probably the orbits of the stars would also do something complicated. So it would be a really elaborate project to come up with how does this work at different times of year? How does this work at different when the stars in different positions in the orbits? And it would be hard. So.
And this is the last one, and it might make our brain melt, but it's a good one. Michael has asked, if there was nobody to observe it, would time exist?
So if there's no, if there's nobody to observe it, does time exist? So that's a question for that's more of a philosopher question. I am by training and inclination an experimental physicist, and so I am very happy to go with the definition of people ask what is time? I said time is what you measure with a clock, and the clock is the thing that ticks, and so time is I count ticks. That's time passing. That's the thing I'm talking about. And something more abstract than that, I don't know what it is. So there are definitely people who argue about these kinds of questions, particularly when you start to bring quantum mechanics into it and things about observation and measurement and the effects of measurement on reality and all this. It goes very complicated places very quickly, but I really don't go with it. I stay with time is what I measure with a clock, and the clock is the thing that ticks.
Keeping it simple. I like
So,
it. So that's all the questions that we've had. So thank you everyone for the brilliant questions that you sent through.
yes, that was fun.
You always manage to fill the times, and thank you, Chad, for answering them.